Hi there, welcome back to another section of this tutorial. In our previous lectures, we did a lot on equations of a line in three-dimensional space. In this particular lecture, we are going to deal with equations of a plane. First of all, what's a plane? I guess you've seen something like this in studies, right? But before then, if this is the first time you're visiting this channel, kindly subscribe, then also watch this video to the end so you understand every part of it. So when we say a plane is simply a 2D shape, right? A two-dimensional space. Any space that you can get two dimension, maybe length times breadth, width times whatever, but it should be a two-dimensional space. That gives us a plane. Okay. So now, when we are dealing with plane, then it means we are in the three-dimensional space or higher space. Okay. So in the 3D space, as I've explained to you earlier, this is our z-axis, this is our y-axis, and this is our x-axis. When you say a plane, in this axis, I can even identify three different planes. That is my xz plane. I can identify my yz plane, my yx or xy plane here. And this is the yz plane. We can also have other planes here, something like this. This is another plane. And this plane is cutting across different planes or different standard planes, right? I can also have a plane acting only this side. So you can get several planes in the 3D dimensional space. So several slices of planes come together to give composite shape of a three-dimensional body, right? If you want to see the shape of a three-dimensional body, it means that it has several 2D portions that has come together to give the composite nature. But that's not the point of interest. Let's get straight to how to find the equations of a plane. Now remember that to find the equation of any geometric figure, we need a direction and at least one point in that particular region, or we need at least 2 points. At least 2 points. In the context of a plane, how do I get a direction for a plane? How do I get a direction for a plane, right? Now, in a plane, in order to effectively determine the direction completely of a plane, we can't use any external vector which we say that it's in the direction of the plane. No, this is not a line, right? So some shape of planes may not allow, but we have what we call a normal vector. A normal vector. Normal vector. So the reason why we can't get a particular vector to represent the direction is within a plane, we have a lot of points within the plane, and we can get different lines in the plane. We can get lines moving this way, and everything is being confined within the plane. So we can't effectively define a direction for all the points within the plane, but we can do using this normal vector. And this introduces us to the concept of cross products. So when you say cross products, so the cross product simply means that the two vectors will produce a resulting vector, and that resultant vector will be orthogonal to any other point in the plane. So let's say in the plane, this normal vector arises up, and this normal vector will be perpendicular to any other point in the plane, and this fully describes the direction of our plane. So whenever we are dealing with the equations of a plane, remember we need the normal vector and we need 2 points or a point in the plane, right? Yeah, so let's start from as we derived the equations of a line here too. I'll have P as a known vector, right? So let me write it. I'll have P, then I'll have P naught. So P naught is a known and P is any arbitrary point in this plane. I have my normal vector N, okay? Yes. And remember that the position vector of P is represented as what? R, and position vector of P naught is represented as R naught, vector R naught, okay? So now, the condition is whenever you find a cross product, the cross product is perpendicular to any other point in the plane. Okay, so meaning that when you introduce the dot product, then remember the dot product of any two perpendicular lines is 0, right? So when I join these two lines, P naught, and I find the vector of that, this vector should be perpendicular to my cross product or to my normal vector. Okay, so at this point I'll say that P naught is the same as, so no, P naught P instead here, P naught P for simplicity here. P naught P is the same as our P. The position vector of P is the same as what? R, vector R minus R naught is another vector R naught for this. So this function expression here is always giving us 0. When you find the dot product of this and our normal vector n, should give us 0. So still deriving our equation, we realize that nr dot n r naught should give us 0. Okay, so this gives us our vector equation. So nr is equal to nr naught. Is that not? So let's represent this with x, y, z, which we don't know, and this with a known. And our n is giving us, let's say, a, b, c, right? A direction vector indeed, because it's giving us the direction of our plane. So therefore, I can have the expression. Let me use this side. So I'll have x minus x naught, right? Okay, I don't know, confuse you, so I'm going to do it this way. My r naught was giving us vector x naught, y naught, z naught. My r is giving us vector x, vector y, vector z, right? And my n is giving us a, b, c, which is a vector. So how do I do that? And this dot product, I hope you remember dot product. So let me do this subtraction. X and x will subtract because they are like components. So x minus x naught plus, let me make it comma, sorry. X minus x naught, y minus y naught, then z minus z naught, right? So this represents this whole thing here. We are subtracting the two vectors. Dots, our vector a, b, c should be 0, right? So dot product is simply that when I take my a and I multiply it by the first one plus b and I multiply here plus c should give me what? 0. So a open bracket x minus x naught plus b multiplying y minus y naught plus c multiplying z minus z naught is giving us 0. And this gives us our equation of the plane. But r minus r naught dot n is equal to 0 is the vector equation of a plane. So this is how we determine the equation of a plane. And let's see, just put these two equations in mind, your vector equation and your, I won't say parametric, but this is a general equation of a plane. So thank you for being with me in this video. We're going to solve a lot of problems in our subsequent tutorials.